All right, so I think we're just about time to start the next session here. All right, so just to make sure that we have enough time for discussion, let me introduce our next speaker, who is Ryan Hamerly, who is a research scientist at NTT, and he's going to tell us all about his talk.
All right, you guys hear me fine, right? Or is this working? Okay. Yeah, thanks a lot, Noah, for introducing me. And I'm going to be going back to optics and talking about dispersion engineering Chi2 photonics for quantum information and light sources. So this talk, as a high-level overview, is going to be about two tools, nonlinear optics and dispersion engineering, which Noah has already introduced you to, and about two applications for these tools, which will be temporal trapping, a mechanism that we hope will enhance the ability to do nonlinear optical quantum computing, and then also frequency comb generation in LPOs. So nonlinear optics, I think a good way to introduce nonlinear optics is to think about what most people think about optics, which is linear optics. So conventional optics is linear, which gives you strong light matter interaction effects quantified by the index of refraction. This makes it non-perturbative, but you also have very limited dynamics that's possible with linear optics. It has to be frequency preserving, passive, and so you can do imaging, communications, filters, linear transformations, but that's about it. Nonlinear optics is a field that involves weak perturbative nonlinearities that only really come into play with high energy and intensity. This is something, though, that once you can reach this regime, many other phenomena, such as frequency mixing, become possible. And this gives you a lot more possibilities. But despite this, the actual productization of nonlinear optics is much more limited. So you have green laser pointers, and then you have a bunch of scientific equipment that most people have never heard of before. And one of the real reasons for that is that the effects are so weak that most people just never encounter them in regular life. And so I wanted to begin this talk by talking a little bit about the origin of nonlinear optics and why it's so weak and the techniques that people employ to mitigate that. So as a field, the discovery of nonlinear optics came about shortly after the development of the laser. So there was first the maser, and then Schlalow, Towns, and Ted Maiman realized you could do this in the optical domain, and so they invented the laser. And the first laser had a gain medium that was chromium-doped alumina, which is ruby. And Ruby is a three-level system. And those of you who know something about laser physics will know that to generate population inversion to get gain in a three-level system, you have to pump it very hard. And so they had a cavity here, and then pumping it was this flash lamp, which as far as a realization, the technical challenges, that makes it more challenging. But once you get this source, you have an advantage, which is it's very high peak power. And peak power is actually just what you need for nonlinear optics. So just 1 year after the first laser was developed, that same kind of a laser was used to demonstrate in a paper by Paul Franken about second harmonic generation in quartz crystal. So this was the first demonstration of nonlinear optics. But it was a very weak effect. And to understand why, you should go back to the equations of nonlinear optics. So nonlinear optics is just an application of Maxwell's equations with a couple of nonlinear terms. If you look at Maxwell's equations, these are all linear, right? And once you add in the constitutive relations, if you assume that those are linear, then all of your dynamics are linear. But the reality is that those constitutive relations are not linear. So usually the nonlinearity comes about through the relationship between the E field and the D field. So D is epsilon naught E plus the polarization. And if all of your charge carriers were in harmonic potentials, then the polarization is just classically, it's a sum of a bunch of the dipole moments of all your elements. And if everything was in harmonic potentials, then you would see that it also depends linearly on the electric field. But because the actual potentials in atoms are anharmonic, you're going to get a nonlinear relation between these E fields and the polarization. And that's what leads to, you can work out the math, it leads to a nonlinear term in this polarizability. And plugging this into a Helmholtz equation, which you get from the Maxwell's equations, you get something that looks a lot like a sourced wave equation. So you have a Helmholtz equation term on the left side, and then on the right-hand side, you have this nonlinear polarization that you get from, well, the nonlinear element in this polarization. So there's some math involved to this. I'm just here giving the equations for plane wave interactions. But if you go through the math, you find that, and make a couple of assumptions, you get what I like to call a master wave mixing equation for plane wave nonlinear optics. So here you have the evolution of a particular frequency term in a particular optical frequency term is going to be a product of three things. One is just a set of constants. One is a phase matching term. And then a third one is a nonlinear polarization. And it's this nonlinear polarization, it's a sum of different contributions. So of course, there's a linear term, which is the strongest effect, but that's strictly linear. And then Taylor expanded out. You have increasingly weak terms, which correspond to increasingly higher order nonlinearities. And for the purposes of this talk, I'm mainly going to focus on this chi2 term, which is for non-centrosymmetric symmetric materials. And this chi2 term, it mediates three-wave mixing interactions. So if you have two frequencies going into a sample, you can get sum and difference frequencies. You can see this because if you look at the electric field and you expand that as a sum of two input frequencies, then the nonlinear polarization, it has, that's just the square of this E field. So that's going to have some frequency terms as well as difference frequency terms, harmonic terms, and then also this interesting DC term, which is a rectification term. Just focusing on the sum frequency term, you can actually write out three-wave mixing equations from this. And what you see here is that in a three-wave mixing process, there are always three processes going on. There's some frequency generation to go from omega-1 plus omega-t to omega-3. And then you have difference frequency generation to go backwards, and these are necessary for energy conservation. And the reason I've gone through this derivation is to show you that these wave mixing equations, they have, in addition to they have several terms. There are the nonlinear terms here, the products of fields. Then is the strength of the nonlinearity. And then there's this phase mismatch term, which comes about from the fact that in order to have efficient nonlinear interactions, you need to satisfy two conservation laws. One is going to be energy conservation, so omega-1 plus omega-2 has to equal omega-3. But the other is momentum conservation, so K1 plus K2 has to equal K3. And in general, you can't satisfy these simultaneously. So phase mismatch is a phenomenon that comes about because you can't satisfy this momentum conservation. Another way to think about this is that if just integrating out, let's say this third equation in the non-undepleted limit, you find that the output field for the sum frequency term is it's a nonlinear product times the strength of your nonlinearity times a sinc function, which is where the argument in that sinc is the phase mismatch term, and then times the length. And then visually, you can imagine that the nonlinear field is a sum of different components at different positions along the nonlinear crystal, and that they're all adding up out of phase. Now you can go through some math and ask yourself, how serious is this phase mismatch? And the answer is very serious. So if you don't make any effort to achieve phase matching, you can show that the maximum intensity for the output of your nonlinear process is proportional to the product of the input intensities, but then it's also inversely proportional to this delta K squared, which is the phase mismatch term. And just plugging in very standard numbers here. So we're taking a material with a high nonlinearity, a reasonably high input power. You find that if you start with roughly a watt of power of input power, then you end up with something like 10 to the minus 10 watts of output power. So you get a conversion efficiency for a native nonlinear optical process without phase matching of about 10 to the minus 10. Now I bring this up because this is what was done in that initial paper. This was not non-phase match nonlinear optics. And the most important figure for that paper was this output on a spectrometer, where they show a big dot there for the fundamental, that's the Ruby laser, and they show a very, very light dot here for the second harmonic. And actually the story about this very light dot is that it's invisible because the reviewers saw that dot and they realized you should accept the paper, and so did the editor. But that when this paper went into production, the copy editors thought that was a smudge, and so they removed it. So the nonlinear optics is such a weak effect without phase matching that it was considered indistinguishable from no effect at all. And so we have to ask ourselves, what can we do to phase match these processes? And a reminder that when phase matching is simultaneously satisfying two conservation laws, both K and omega. And that you can't do this in general because your dispersion relations are bent, or K is a nonlinear function of omega. And this is what leads to this delta K term that you're getting here. So one way to do this is if you have two dispersion relations, one for K1 and K2 and a second for K3, then you can get what's called birefringent phase matching. And this was the first one to be employed, first technique to be employed. And it increases the efficiency of these interactions by orders of magnitude. You can see that because what you're doing here is you're taking the sync term, which normally will decrease with the length of your crystal, and you're basically setting that to 1. So this very small number becomes 1, and then suddenly your conversion efficiency goes way up. And not only that, but the scaling with the length of the crystal also goes up because you have this L squared here. You do have some downsides associated with spatial walk-off in this case, as well as diffraction, which means you don't quite get this L squared scaling. You get more of an L to the 1/2 scaling, but it's still much, much better, orders of magnitude better than not having any phase matching. So a second advance was predicted all the way back in this paper in 1962 by Armstrong and Blumbergen. And this was 1 year after the first experimental demonstration of nonlinear optics. So just 1 year afterwards, these gentlemen worked out basically all the fundamentals of three-wave mixing interactions. It was a theory paper at the time. And so being theorists, they were able to conceive of many things that were later realized experimentally. So these included other mechanisms for phase matching, such as phase matching in cavities, phase matching between different modes in a waveguide, and also this technique called quasi-phase matching, which is where you add in a lattice momentum by periodically inverting the sign of the nonlinearity to compensate for that delta K, or that phase mismatch. And actually, Blumbergen was one of the pioneers of nonlinear optics, and for this, he won the Nobel Prize. We would say that Armstrong, he sort of upstaged him by going to the moon, but actually that's a different Armstrong. So, what? Yeah, so quasi-phase matching, that was just a concept, but later on, this was realized experimentally in ferroelectric Ki2 materials. So these are materials like KTP and lithium niobate that where the nonlinear polarization is due to the ferroelectric symmetry breaking. And so you're able to, by applying strong coercive electric fields, you can force this symmetry breaking to go in one direction or another. And so what people do is they'll start with these crystals, and then they'll deposit these periodic electrode patterns onto them, and then apply a large voltage across those electrode patterns to inscribe basically any QPM structure that they want. So they can get any phase matching relation that they want up to the fabrication precision, and I guess the polling precision of this process. And so quasi-phase matching, that was another big advance in nonlinear optics. It means that now you can phase match the same polarization, which is much more convenient. And it also increases the efficiency, and in particular, the scaling of this efficiency, because now you don't have this modal walk-off anymore because you're just phase matching the same polarization. The next advance came when people realized you can also inscribe waveguides into these nonlinear materials. This was first done with mechanical dicing and ion diffusion. A lot of that work was done here at Stanford. And that ends up giving you waveguides in both processes that are about 10 microns or so in size. And in the last decade, people have also realized how to do this with wavelength scale waveguides. So this would be through ion slicing techniques in lithium niobate plus low roughness dry etching. And it's the waveguiding which it actually increases the efficiency by a couple more orders of magnitude, and it fully restores this L squared length squared scaling of this conversion efficiency, or the strength of the nonlinearity. And the reason now is that the size of your waveguide, the interaction area is not set by the length of the crystal anymore. It's set by the cross-sectional area of the waveguide. So where does dispersion engineering come into this? It comes into this because everything that we've talked about here, all of this phase matching discussion, it only applies at a given frequency. And if you're interested in broadband interactions or ultra fast interactions, then you care about phase matching not only at one frequency, but at many frequencies. And in addition to that, dispersion engineering is really critical for other dynamics such as pulse spreading and soliton formation. And dispersion, it's going to be a function of two things. One will be materials, and the other will be geometric. So why, just an example of why dispersion engineering is important, and I pulled this figure from a paper from some of our collaborators over at Stanford, is that just looking at any nonlinear process, the phase mismatch term, that's going to be a function of frequency. And so with quasi-phase matching, you're able to set that to 0 at a given frequency omega. But now if I scoot over to just another frequency, omega plus big omega, then you can see that delta k, you have to expand out the k of omega. And then what you get here is a term that depends on the differences in the group indices times your delta omega. So basically what this says is that to achieve broadband phase matching, I need to control the dispersion of the waveguides through which my light propagates. And if I don't do that, then the bandwidth of my interaction is just going to be very narrow. So how do we do that? Well, one, if you had infinite resources, you could just explore many different materials and find a material with the right dispersion. Every material will have different dispersions, usually governed by some kind of a Sellmeier. But usually what you find is that they all have similar universal properties. So the index is always going to increase with omega. You tend to have normal dispersion over most wavelengths, and then you also have this dispersion slope is always positive. And if your dispersion engineering was only set by your material, then every time you want a new dispersion, you would have to work with a new material, and of course that's many years of fabrication work just to get that working. So fortunately, in these waveguides, we also have something called geometric dispersion, and this is a programmable form of dispersion. And this is something where in a waveguide, you have a dispersion relation that couples your core to your cladding. And so it's going to be core-like at short wavelengths where it's tightly confined, and it's going to be cladding-like at long wavelengths where it's loosely confined. And what you can see from this is that this means that the line has to interpolate between the dashed curve and the dotted curve. And so you're going to get a point where the slope is highest, and that's going to correspond to a peak in the group index, which also corresponds to a 0 in the group velocity dispersion. Okay, well, you can also get 0 GBD in native materials, but what's interesting here as well is that the dispersion slope is negative. So on to the blue of this 0 dispersion point, I get anomalous dispersion. Into the red, I get normal dispersion, which is opposite of what you normally get in materials. And what's really critical here is that the frequency at which you get this 0 dispersion is set by the waveguide, which is just waveguide dimensions, or the geometry. So this is something that you can just program in rather than having to invest 10 years in developing a new material system in order to get a new dispersion. And this is just an example of how you can use dispersion engineering to satisfy a number of criteria. In this case, this was work that was done by Mark Jankowski about looking at broadband second harmonic generation. So for broadband second harmonic generation, you want to match group velocities as well as minimize the group velocity dispersion at both of your harmonics. And by tuning two parameters in this standard lithium niobate layer stack, you're able to satisfy all of those conditions approximately. So in terms of the energy scale of nonlinearities, dispersion engineering lets you achieve nonlinearities across a broad bandwidth, which means you can use short pulses to it. And short pulses means that since the nonlinear interactions depend on peak power, you can use less average power or less average energy. And I should also mention that dispersion engineering is not a technique that's unique to lithium niobate, which is what we're pursuing a lot at NTT research, but it's present in many materials. In fact, first it was studied in silicon nitride, and then these Chi2 materials started, the fab was developed for photonics in those materials as well. So now I want to talk about some of our research results, which will be two applications of dispersion engineering nonlinear optics. One will be temporal trapping, and the other will be OPO mode locking. So I'll start with temporal trapping. So this part of the talk is about quantum computing with nonlinear optics, enabled by a new trapping mechanism to confine light in time. Currently, this is a theoretical result. I'm going to talk about simulations of gate fidelity, as well as an analysis of the dispersion engineering you need in order to make this all work. And putting this together, you have what I hope is a plausible new approach to quantum computing, although I think this is very long term. So in optical quantum computing, you have a qubit, which is usually realized in a dual rail basis. And in this basis, single qubit gates all reduce to linear optics. But you also need an entangling gate. And this requires some kind of nonlinearity. So this is an example of how you would realize that with a Hongo-Mandel interferometer plus this U-pi thing here, and that's a curve phase operation. And this curve phase operation is the hard part in optical quantum computing. There are multiple ways to do this. You can achieve it in a heralded manner with the KLM protocol. This is called linear optical quantum computing, but heralded gates have a big, resource overhead because you need to convert those into deterministic gates. Or you could do it with some kind of a strong nonlinear optical interaction. So if you can coherently achieve this U-pi through nonlinear optics, then you would get deterministic gates. But then this requires a strong nonlinear optical coupling. So this is the trade-off that you have to play when you do optical quantum computing in this basis. Now you might say, you might say that this is just a problem of discrete variable computing. And if we work in the CV systems where entanglement is easy, it's just squeezing, then all the problems go away. And that's true as far as the entanglement is concerned and the entangling gates. But for the CV protocols, you still need to generate non-Gaussian states like GKP states. And here you also run into this trade-off between linear and nonlinear optical quantum computing. So as a result, having a strong single photon nonlinearity that would avoid the overheads associated with LOQC would be very useful. And there are several effects that have been pursued to bring nonlinear optics down to the quantum limit. So I guess I'm viewing optics very broadly here. If you look at in the microwave domain, of course, we already are there with superconducting circuit QED. And we're also already there in the quote real photon optical regime with defects like quantum emitters or atoms. But that's something where scaling it up is extremely challenging and it still has to be cryogenic. On the other hand, bulk nonlinear optics is scalable in room temperature, but the effect is orders of magnitude weaker than either of these other two effects. But we want to pursue if that's possible. So to get strong coupling with bulk nonlinear optics, we're going to need two things. One will be strong optical confinement or a small mode volume, and the other will be good phase matching or very long photon lifetimes. So let's look at two approaches that have been pursued to reach the quantum limit. To start, we can consider a cavity. So here we're aiming to amplify a weak nonlinearity with spatial confinement in phase matching, which you can do by shrinking that mode volume as far as possible with a photonic crystal, or you can do by increasing the Q factor as far as possible with ring resonators and tolerating a slightly larger volume. But usually you can't do both things at the same time. Also with the photonic crystals, it's very hard to realize Chi2 nonlinearities in them because the second harmonic doesn't resonate very easily. And in these rings, the mode volume is a couple orders of magnitude larger than the wavelength limit. So unfortunately, in both cases, you still don't get all the way to this strong coupling regime that we want for optical quantum computing. So let's consider a second approach, pulse nonlinear optics, where you're maximizing temporal confinement in a phase match structure. So this is, I guess, motivated by the progress of different generations of nonlinear optics, where we have dispersion engineering here at the end. Unfortunately, though, even with the best experiments to date, you're still looking at nonlinearities at a femtojoule scale with dispersion engineered waveguides. And so that's 10,000 photons or so, which is still orders of magnitude away from this single photon regime. So what we're proposing doing is to combine these two approaches and look at interactions between pulses in a cavity. If you can interact pulses in a ring cavity, then theoretically you're reducing the effective mode volume from that of the cavity to just that of the pulse, which is close to a wavelength. And equivalently, you can think about this as a dispersion-engineered nonlinear interaction, where the waveguide is now not just limited by physical fabrication lengths, but can be as long as the photon can propagate around this ring cavity. So just limited by Q factors. And so theoretically, if you do the numbers, and some of our colleagues at Stanford, Edwin Ng, and some people in Hideo's group did this analysis earlier, we found that it does look like you can get to this limit, but there are a lot of challenges. And in particular, one challenge is practical, which is that it requires very unrealistically small dispersion. Otherwise, these pulses will just spread out over their lifetime. And a second is that the nonlinearity itself is distorting the pulse shapes during the course of this nonlinear interaction. And it's the second one, which was predicted all the way back in 2006 by this paper by Jeff Shapiro et al., which is it's related to the fact that the interaction that you're trying to achieve here is not acting on single mode systems. It's acting on systems where there are many modes. So if I have going into this nonlinear operator here, I have some pulse going into that. And it's a pulse with 2 photons. What does a 2 photons pulse look like? Well, a 2 photon pulse, it's going to be a wave function, which is a function of two times. You're going to have 2 annihilation operators here and then the vacuum. Now, what you want is to start out in a separable state like this, where psi factorizes, and apply a given nonlinearity, and get the same separable state out with a pi phase shift. But what you actually get with this nonlinearity, and the best kind of dispersion engineering for this interaction, is going to be something that looks like this. So that's not a separable state, and it gets you part of the way, but the fidelity is still too low to do any kind of gates. So this is a very fundamental problem in pulse nonlinear optics, and it happens because in pulse nonlinear optics, your pulse is not really an eigenstate of a basis. It's just a wave function, and that wave function can disperse, and even if there's no dispersion, there's no reason that the dynamics should prefer that wave function over other wave functions. So what you need is a mechanism to confine the light into a fixed pulse, or what we would like to call trapping a photon in time. So how do you trap a photon? To motivate this, I think let's consider the normal modes of an ordinary ring cavity. So most cavities have dispersion, and dispersion functions as a filter, only allowing certain nonlinear processes and to resonate at a given time, which is great for CW dynamics. You can also use it for tunability. But the modes that you get out that you can interact spread out over the whole cavity. So this doesn't work for pulse nonlinear optics. So dispersion engineering does enable pulsed interactions. And you can think about what's happening here is that if you zero out the leading dispersion terms, then in a co-moving basis, all the modes are degenerate. And when that happens, there's no preferred basis set. So you could equally well have started with a basis set which consists of a pulse like this, as well as other modes that are orthogonal to this pulse. So at this point, it looks like it'll work, that we can engineer an interaction between that pulse mode, that's the second harmonic in green and the fundamental, and we can get a reduced effective mode volume. But what's happening here, and this is just a restatement of the Shapiro problem, is that all those other modes still exist. And the nonlinear interaction, even if the linear interactions don't couple everything because you have perfect dispersion engineering, the nonlinear interaction still does couple everything. And so you still get a poor gate fidelity as a result of those spurious couplings. So the technique of temporal trapping that we're proposing here is that you still have some small amount of residual dispersion, but you add an additional term that's not present before, which is going to be you inject this additional pulse of light called a trapping pulse, and that pulse goes around in the cavity, and through cross phase modulation, that induces a time-dependent phase shift. And that time-dependent phase shift has the effect of lifting this degeneracy by preferring some modes over others. And as a result, a single mode pair can be filtered out from the rest, and any leftover dispersion or nonlinear distortion in the system gets suppressed because it's coupling to things that are already highly detuned away from the resonance. So we have performed some numerical simulations to see how much trapping you need to get good dynamics. I'm going to start here with the model. Here we're going to have a ring cavity with an E field, which is a sum over normal modes. The Hamiltonian has linear chi2 and chi3 terms. And then from this, you get Heisenberg equations. And from these EOMs, you go into a rotating waveframe, you perform a Fourier transformation, and then you get a Lugiata-Lefevre equation for the intracavity waveform, which consists of terms for both external coupling, dispersion, the chi2 nonlinearity, and then this additional trapping term. So we can rearrange these equations for the fields that we care about, the fundamental and second harmonic, and you see they contain terms that are linear in A and B and then nonlinear. And the linear dynamics, it can be reduced to a Schrodinger equation, where the momentum term is given by the dispersion in your cavity, and the potential term is given by this cross-phase modulation for the trap. And when you have a Schrodinger equation with a potential, then it's easy to see that depending on how you set that potential, the eigenmodes can either be bound or unbound. So if you don't have any trapping field, then you'll just get eigenmodes which are sine and cosine. So this would be in the lab frame, and this would be in the rotating wave frame, where the curvature of this potential is given by the group velocity dispersion in the waveguide. When I add in that trapping term, though, what that does is it creates a bound mode, which is separated from the rest of these continuum modes by an energy gap. And this you can also see through an analogy to a soliton. So dispersion is spreading out a pulse in a soliton, and Kerr nonlinearity, self-phase modulation usually stabilizes the shape of that soliton if your dispersion is anomalous. But in this case, we're using the cross-phase modulation from the trap rather than self-phase modulation from our signal, which only has 1 or 2 photons. And that's creating this stable bound state. And then this also sets conditions for your dispersion. So if you're trapping with a bright pulse, you need anomalous. And if you're trapping with a dark pulse, you need linear. Normal. And so let's simulate some quantum gates with this model. So remember, we want to implement this CZ gate with this Kerr phase operation. The way you do this Kerr phase operation is with this chi2 cavity. You're loading this cavity at the fundamental with either 0, 1, or 2 photons. And if there are 2 photons, then you have this mode splitting between the 2 fundamental photon state and the 1 second harmonic state. And you wait for 1 Rabi period for it to oscillate, and that oscillation accrues a pi phase shift. So we can see how this works with different trap depths, starting with no trap at all. So what's happening here is that I'm injecting one fundamental photon into it, or 2 fundamental photons into it, and it's up converting to a second harmonic, and then it's sort of down converting and also spreading out all over the place because there's no trap. And if you look at the Rabi oscillations for this, and this is we've engineered the dispersion to give us the optimal Rabi oscillation. You can see that it's basically only half of an oscillation. So this is not useful as a gate. But even adding a weak trap, so this is a trap with a strength comparable to your nonlinearity, which is already very weak. You can see that you've already are getting dynamics where the oscillations are much higher in fidelity, and increasing the depth of that trap, the fidelity of the oscillations goes up still further. In fact, you can relate the gate fidelity to the depth of the trap through an expression whose scaling is consistent with second order time-dependent perturbation theory. And what this means is that if you have strong enough temporal traps, that you can engineer effectively single mode interactions here that can get around the Shapiro problem and give you high fidelity gates. So this works in theory. Now let's bring it down to earth with some dispersion engineering. So what do you need in order to get temporal trapping? You need to satisfy several conditions. First of all, you need to match the group velocities of your fundamental and second harmonic. They need to have the same sign of dispersion, so you can trap both of them. And then you also need this additional frequency, this trap frequency. And that needs to be something where it should be the wavelength should be longer than the fundamental and second harmonics, so it doesn't pollute them with Raman, and also so that it couples out of the cavity more efficiently, so it basically is not resonant. And then it should also be a frequency that doesn't have too much of a group velocity mismatch or too much group velocity dispersion itself over the round trip of the cavity. And you can actually, so going back to this standard lithium niobate stack, that there are conditions where, or there are geometries where all four of these conditions are satisfied. We are optimistic that this is something that's will not just remain a theoretical concept forever, but can be realized in the near future. And with such structures, if you plug in the numbers, you can show that you get pretty close to strong coupling. So already people have gotten this G over kappa ratio to be about 0.01. And that was with Q of about 10 to the 6. 10 to the 7 is very doable these days. So 0.1 is probably doable with rings without any trapping. This trapping is effectively reducing the mode volume from that of the ring to the volume of the pulse itself, which is basically the duty cycle. And you can get that down by, we estimate about 2 orders of magnitude, and that increases this G over kappa by about 1 order of magnitude. So we think that there's a plausible path to getting to a G over kappa of 1, which is just at the threshold of strong coupling. And that's probably not good enough for quantum gates, but fortunately, a lot of these things improve if you're able to scale down the wavelengths to much shorter wavelength interactions. So you can actually show that the scaling of G over kappa has a potential to go as lambda to the -3. And that means that instead of working with a 2 micron to 1 micron process, you work with an 800 to 400 nanometer process. And lithium niobate is still transparent at 800 and 400. And there are groups that have demonstrated low loss at 400, but 500, 600, that there might be a plausible path to achieving things that really are strong coupling with this approach. And I guess to put this in perspective, I've just had this plot here comparing the trade space with the coupling on the y-axis and the loss, or basically the Q factor, on the x-axis. And you can see that there is a trade-off with most conventional approaches. There are ring resonators, there are whispering gallery mode resonators, there are photonic crystal cavities. But usually if you increase one thing, like the Q, you're sacrificing something like the coupling or the V. And our hope is that temporal trapping would enable you to reach this corner of the trade space that everyone wants to operate in. So that's more of a long-term goal of us. Ours is realizing these quantum gates with dispersion engineering, but I can get to a short-term goal, which would be realizing frequency combs with OPO mode locking. And so this is something where it's more of a classical application, but it has a lot of uses. So as the frequency comb it's an important and versatile tool in optics. It was actually something that won the Nobel Prize back in 2005. But there are many applications that go beyond just the precision spectroscopy that won this Nobel Prize. There are things in communications, LiDAR, and then also some emerging fields like coherent Ising machines. And a lot of these emerging applications, they're very cost constrained. So you can win a Nobel Prize with a lab bench, but you're never going to make a commercial LiDAR system that fits on a bench. So there's been a lot of this effort towards miniaturization of frequency combs. And as a result, partly as a result of this miniaturization, people have discovered that there are a lot of challenges to making practical frequency combs. These include efficiency, turn-on dynamics, spectral flatness, tunability, and also dispersion. And this motivates work into unconventional combs based on OPOs, where we're looking at this quadratic nonlinearity, or this Chi2 nonlinearity, which, if you look at CW OPOs, it's already very nice because it's broadband and it's tunable and it works at high efficiency. There's been a lot of work into how you would take the CW dynamics and also make it work at many frequencies simultaneously. And one paper that I think really stands out in this is the idea that we just CW pump the OPO, and by putting, or we take a CW pumped OPO and you put a phase modulator in the cavity. And this was something that it was first proposed as a concept and also implemented in 1999, but this has there's been new advances in this field with thin film lithium niobate, and there was this great paper by Amir's group just earlier this year. So before getting into our work, let's review a wish list of properties we'd like from an OPO cone. These include tunability, both in the bandwidth and the center frequency, ideally over a wide range, high efficiency, which is possible in CW OPOs, but by no means guaranteed in a cone. And then it should be cheap and robust, which ideally means it should be CW pumped if it's an OPO. It should be singly resonant and have turnkey dynamics. And finally, something that's broadband, with a goal being something that's in principle possible of scanning an octave, possibly through the use of chirped QPM, like what Noah talked about earlier. So this talk is going to introduce one of our proposals, which is called the QAM OPO, which is a new type of frequency comb source formed by hybrid AM and FM mode locking of OPOs. So in a conventional OPO, in a conventional EO comb, recall that you have a cavity, and that cavity is pumped somewhere on resonance. And there's a phase modulator in that cavity, which is matched to the FSR, which couples this power to neighboring modes so that you get this set-shaped comb. In an OPO comb, you're pumping that cavity at the some frequency, and then that pump is generating a signal in an idler. And then we're going to phase modulate that signal light, and that's going to generate a comb at the signal frequency, and you also get a comb at the idler frequency. Now, what we're going to do a little different here is that modulation is going to consist of a cascade of an intensity modulator and a phase modulator. Or equivalently, you could say it's a dual drive Mach-Zehnder, where you drive both of the arms with different phases. And we're going to show that with this hybrid mode locking scheme, that the steady state output looks like a highly chirped pulse, whose dynamics are governed by an interplay of gain and intensity modulation, which limits the pulse width, phase modulator chirp, which red and blue shifts the tails of the pulse, and then also dispersion, which is pushing the tails away from the center. Yeah? Oh, 5 minutes. So we end at 45 or we end at 45? Okay. Okay, yeah. Yeah. So we're going to model this nonlinearity using an Akita map, which is a, wait, it's 2:28. So 5 minutes until questions or what? Yeah. Okay. Yeah. Okay. Yeah, we're going to model this nonlinearity using an Akita map, where each ground trip is going to consist of chi2 gain, modulation, and the lumped element dispersion term. But we can get a more intuitive picture of what's going on by constructing a reduced phase space model. So here we're going to take the same system and construct a phase portrait with time on one axis and frequency or wavelength on the other, and ask ourselves what each step in this Akita map is doing. So the phase modulator chirp, that's going to give you a time-dependent wavelength shift, whereas cavity dispersion is giving you a wavelength-dependent time shift. And you can combine these effects to trace out curves in phase space according to some dynamical model whose streamlines are shown here. And for this simulation, I'm assuming very generic properties for free space, such QAM OPO, but this would also work with integrated. So finally, this is an OPO, so it has gain, and the gain is going to be limited by phase matching, so it's wavelength dependent. And you're going to have loss that's time dependent because that's set by this intensity modulator. So those things trace out a gain region in phase space. And this could all be made more rigorous by making a chirp pulse ansatz and showing that everything reduces down to a first order PDE, which can be solved with the method of characteristics. But let's see how this works in practice. So here we're running the QAM OPO. This is all numerical simulations and showing the intensity, the power spectrum, and the spectrogram as the field is building up. So notice how we started with vacuum noise, which got amplified through all of the gain region, but that amplified vacuum noise was sheared by this phase space dynamics until the signal basically resembles a tripped pulse with some glitches, and then those glitches get pushed away until you're left deterministically with this stable broadband chirp pulse. And that pulse emanates from a saddle point of the dynamics and lies along a separatrix in phase space. So the physics of this OPO directly maps to, or the phase space physics directly maps to an inverted pendulum to the inverted pendulum model to leading order if you only consider quadratic dispersion and a sinusoidal drive, which is great because inverted pendulums have been heavily studied in classical mechanics. And it also gives us analytic expressions for things like the dimensionless time constants or the characteristic scales for time, frequency, and the number of round trips needed to reach equilibrium. So the previous case involved a case of stable comb operation. The comb operation requires navigating a minefield of instabilities, each with which places constraints on the device. For example, let's say you wanted to get rid of the amplitude modulator. Then bang, you'll hit something called wraparound instability, which happens where the tails of the pulse wrap around the cavity, leading first to fringes and then outright chaos. Or if you get greedy, and add too much dispersion compensation, you get something called loopback instability, where the separatrix loops back on itself due to this higher order dispersion, and the vacuum fluctuations build up to the left of the loopback. And also, if you try to make the comb broader than your gain bandwidth, you get what's called a mode hop instability, where the center of the pulse is stable, but the tails suffer from large fluctuations. And we have models to understand each one of these. The wraparound instability, you can model that with basically a WKB expansion outside of the gain region. And you actually get a formula, which an analytic formula, which is very close agreement with the numerical dynamics of these combs in this instability regime. For loopback instability, you can expand dispersion. If you expand dispersion to third order, you're going to find that your delta omega curve, basically the integrated dispersion, is bending over. And this is something that people in the Kerr comb community have realized for a long time. And this gives you but for this quam OPO, what this does is it gives you a maximum bandwidth and a maximum phase modulator drive. And the concept of this loopback is very closely related to dispersive wave emission, which in Kerr combs or Kerr solitons, this dispersive wave forms at basically this point C here, which is the top of the loopback. And finally, mode hop instability, it's arising from a common function in OPOs, which is that if you seed at the wrong wavelength, the OPO is unstable, the fluctuations at higher gain modes. And the same thing can happen in the quam OPO, but the phase space dynamics are working in your favor here because they're pushing those fluctuations outside of the gain region. So you can put all these things together and you find that there are three figures of merit that you can satisfy in order for stability to get stability with respect to each of these effects. And following those criteria generally gives you stable comb formation. So I mentioned that tunability is really important for some applications for frequency combs. And one great thing about this comb generation mechanism is that it's RF tunable. So to understand what I mean here, recall that in the phase space picture, the comb is centered at this saddle point, and the saddle point is given by these two equations. Now, let's add some detuning to the RF frequency that drives the comb. So if I drive the EOM at a frequency that's slightly different from the rep rate of the cavity, that basically gives you an effective group delay dispersion. And that group delay dispersion, it shifts the point, it shifts the saddle point up and down in wavelength. And so here are some simulation results showing that by tuning this FREP by 2%, you're able to shift this comb over the entire gain window, which if you consider both the signal and the idler, basically spans a whole octave. Now, since this is a chirp pulse, of course, it's pretty obvious that you can just undo that dispersion and generate transform limited pulses. That's something that we've analyzed. This, I think, would be good to realize, but at least the analysis shows you can get pretty close to it, even if you only correct for second and maybe at most third order dispersion. And finally, I think I'll skip over some of this because Noah already talked about chirp dynamics, but you can do the same thing for these quam OPOs, and you see that actually with the frequency comb generation, you're able to stabilize this OPO dynamics, which is not normally possible for CW pumped chirped OPOs. I think I'll skip over this for lack of time too, and then just conclude here. In conclusion, I presented two things here, and they're both applications of dispersion engineering and nonlinear optics. One is a quantum application, which would be temporal trapping to achieve higher nonlinearities, which get you closer to this strong coupling for nonlinear optical quantum computing. And the second is OPO mode locking through this new hybrid AM-FM mode locking mechanism that gives you frequency combs with good properties in terms of the tunability, the pulse generation, and use with chirped OPA. So if you're interested more, we have the results of this talk are mainly in those top two papers, and we have a number of other good background papers. There's one by Mark Jankowski about dispersion engineering. There's one by Rajveer, who works with Ryotatsu, who's giving a talk later about some strongly coupled Chi2 nonlinearities. And then Mark also has this great tutorial of quantum nonlinear optics. And then Ryotatsu also has this great tutorial on really stuff that he's going to talk about later, which is about mesoscale, the mesoscale dynamics regime of NLO. All right, and that's all.
Let's thank the speaker. All right, any questions? Start with Gaeta.
Ryan, for the temporal trapping, the input pump pulse, I guess, your yellow pulse, if you want to call it pump pulse, is that matched to be much narrower than the cavity line width? What are its properties? Because you didn't talk much about the input-output coupling, but I'm sure it's all included in your model.
That's important. So first of all, I only show one pulse in that picture, and I've actually thought it would be very useful for pedagogy to make that a movie rather than a picture. But movies take a lot of time to make. But it's actually a pulse train, and that means that you're inside of that cavity. For every round trip, you have one pulse that's propagating through. So you could, if the cavity was high finesse at that trapping field at the frequency, it wouldn't really matter. The input will be a comb that will be matched to the FSR or matched to the FSR of the cavity. But I think that for practical points of view, you probably wouldn't want that, because the whole point of this temporal trapping is to generate a strong cross-phase modulation interaction. So if you do that, you also have self-phase modulation. And so this could lead to a lot of nonlinear dynamics in the trap pulse that you don't want. So I think what's better is to have the trapping field be because it's cross-phase modulation, it'll work at any trapping frequency. It should be at a long enough wavelength that the trap pulse couples out very efficiently on every round trip. So it's basically not even a cavity at all. Or if it's a cavity, the Q is orders of magnitude less than at the fundamental.
So the coupling is designed differently between all pulses?
Well, if you think about it, if it's a directional coupler, and it's also important to note here that you only ever couple into and out of the cavity at the fundamental frequency, not at the second harmonic. Second harmonic only exists inside of the cavity to give you that nonlinear interaction. So because of that, that significantly makes your coupler design significantly easier than stuff like what Amir has had to do for the efficient SHG or OPO experiments, where you have to couple out both frequencies. In that case, if you just use a standard directional coupler, if the trap field is at a longer wavelength, it'll couple out much more efficiently.
So was a little bit fast for me. I just trying to understand what, I mean, from the equations, I couldn't really see how it's, how can we see it as a trapping procedure, this cross-phase modulation, actually. So when you go to the equation that you had written, I don't know which slide was that, somewhere in the middle, but for the trapping temporal, yeah, that's it, yeah. So how do we see that? I mean, and
yeah, so these equations, these are dynamics that are governed by this Hamiltonian. So if the D here to first order, that's quadratic in that. So you can think of the D squared over dt squared. So dB dt is minus I, some dispersion, d squared psi over d squared b dt squared. That's just going to be the momentum term in your Schrodinger equation. And then this gives you the potential term. So I think it's important to emphasize that this is not trapping the pulse to a particular point in the cavity. The pulse is always propagating around the cavity. It's it's only trapping if you think about it in a co-moving basis, which is moving at the speed of the trap poles.
I think we might have time for a little bit more. Yeah, let's start with Amir here.
Thanks, Ryan. Actually, this is a good page. So I was just wondering, what kind of refractive index change are you talking about for that cross-phase modulation to have a good trap?
So it can be very, very little, because if you, in the simulations that we did, we showed that you can get if reasonably high fidelity in these gates, if your trap depth is something like 3 times, if that delta, which is your trap depth, is 3 times g or so, and this g is the single photon nonlinearity. So this is chi2 and not Kerr, so I can't put a number on what that will be, but this is a very, very small effect.
So this is like, I think this would be like 10 to the minus 8 refractive index or something. Just like because if your Q is 10 to the 7 and your nonlinearity is on the order of the Q, then you.
Yeah, that's a good way to put it.
Yeah. So but I can get that kind of refractive index change with lots of different ways. Like it seems like using solitons is a hard way of getting that kind of refractive. Like I could use electric fields in a with a some sort of traveling electric fields, or I can even project laser field that goes around that generates this kind of trap.
This is actually something where I was talking to some people over in DTU a couple weeks ago, and they said this looks a lot like what the time lensing people have done, where you have, I think you have these ring cavities where there's some dispersive, just a fiber section, and then a phase modulator, and the phase modulator gives you also a time dependent phase shift, and there you do also stabilize the modes of a harmonic oscillator. So that will be you can do that, and also I think Ryotatsu has done a little bit of work in this direction as well. But the challenge is you'll always be limited to the bandwidth of your RF field, and that will you can drive harder, and that makes the parabola steeper, but it's the eigenmodes are always going to be comparable to 1 over the frequency. So if the frequency is 10 gigahertz, then you're looking at tens of picoseconds, 100 gigahertz, maybe a couple picoseconds. But getting to this tens of femtosecond with RF traps seems very challenging. I'd be open to discussion if you think that is a feasible way, though.
So we'll go to Schuster and then.
Yeah, so you mentioned as one of the motivations is for doing optical quantum computing, and I've always been fascinated by this because we're nominally doing photonic quantum computing, but our photons aren't real apparently, and so I've always wondered about it, and we use a lot of the same words, but I'm not sure if they even mean the same thing always. So, like for example, you were kind of at the end, like sort of saying that using kind of a cooperativity to sort of say like, okay, we could be at like 1, or maybe we could get to, even past that. And I don't know if it's the same in this case, like for us, like like your gate fidelity is roughly kind of like, the error is like 1 over a square root of cooperativity or something like this. And I was just kind of curious, like what do you think is there a consensus in the community of like, what like cooperativity or thing like that would you need in order for things to work well? Because we have like a really high cooperativity, but we're still like struggling. So I was just kind of curious how that works. Maybe we're doing something wrong.
Yeah, that's something I think about too. I don't have a good answer to that. It seems like the community consensus has been that optics will not work for quantum computing for that reason. And this is why the leading approaches to optical quantum computing involve heralded gates. like what Psyquantum's doing or what Xanadu is doing with their Gaussian boson sampling to generate GKPs. We were pursuing this because I think it's very interesting to ask the question, what if it was possible? And also, I think I've talked to some people about there's an interesting question of if you had a little bit of nonlinearity and then also had other resources that in optics are much more straightforward, like let's say single photon detection plus a close to strong coupled nonlinear interaction. If that would enable you to do something that is kind of a hybrid between LOQC and NLOQC. So there are some people that have looked at what kind of nonlinearity you would need in cavity QED systems to get more efficient Bell state analyzers. And apparently, if you have cavity QED systems with arbitrarily high cooperativity, you can also do deterministic gates. But even if you have only moderate cooperativity, you can use that as a resource for more efficient Bell state analyzers than what you would get just with linear optics. And apparently that would be a very useful resource for optical quantum computing.
Yeah, maybe relatedly, so Amir's he walked out, so I can say anything I want. So he's totally going to make a transducer that's going to work perfectly and be able to convert any of the things we can do in the microwave, in the superconducting systems up to optical, let's say, because he's not here. So he can say he promised. So if let's say we could make you guys, some like, I don't know, decent-ish GKP states, like, the ones that have been made in the superconducting and just have a supply of those, would that would that help or would that, would it make sense, or is it actually would be like mismatched in such a way that it wouldn't really help for these other schemes where they're using the resource states?
Or would that replace the need to do strong nonlinear optical nonlinearities?
I was just wondering, is there any way that being able to prepare states reasonably well, like with that in one domain and then just move it up, would that be helpful, or in the end, like the resource that you have, like it's so mismatched in terms of speed or something like that it would end up being like not that useful?
Yeah, I can't answer that here. I think that is a good question worth talking about more in the future.
It's great and exciting. The rest of it seems to be very straightforward, much more straightforward than in CQT. Saying the rest of the source, with the class, you need the combination with the cluster states. But with that, I think you have a lot of scalability with the GKP.
Thank you. All right, I think that's about the time we have for questions for Ryan. So if you have any more questions, you can ask him during the coffee hour. And otherwise, let's thank him one more time.